moving up in the world. All right, buffers. First of all, we have to know what a buffer is. Anybody have a clue? Yeah, that's what a lot of people say is it slows down the reaction. It doesn't really slow it down. Anybody use buffers in biology? Maybe, but I don't know what they do. What? No. Tums? Sort of. Okay. All right. Buffers do. No, I don't know that. Anyway. Well, the Tums or whatever are going to neutralize stomach acid, but it could be a buffer, but to but those I don't think are anyway. A buffer resists. Let me just explain. A buffer resists a change in pH. So it's important in your bodily systems, right? Because doesn't your blood have just a 0.2 difference of the way it can swing for your pH and you still live kind of thing? Yeah, it's really small. So there has to be a buffering system in there. And so in other words, if you put a strong acid or strong base into a buffer, it's not going to change the pH as much, right? It's only going to change it very little. That's kind of the function of a buffer. What makes up a buffer is it has to be a pair. It has to be a weak acid with a salt that contains that weak acid's conjugate base. Okay, if that makes any sense. So a weak acid with a salt that contains that weak acid's conjugate base. Or it has to be a weak base with a salt that contains that weak base's conjugate acid. It's conjugate acid. All right, so let's write an example. Give me a weak acid. HNO2 is a weak acid. What would be a salt that contained its conjugate base? NaNO2. So a combination of these two things in a solution would be a buffer. All right, give me another one. Another weak acid. Yes is not an answer. What? Okay, the do now one, was that a acid or a base? That was a base. We can do that one for the base, which was it was an ethylamine. It was C2H5NH2. Is that what it was? All right, so this is a weak base. What would be a salt with that in it? Yeah, that becomes much harder, doesn't it? Because you don't recognize that. The weak base is salt. The conjugate acid will be the cation. With what? Right? It has to be with an anion. Okay. All right. So go back up here to another weak acid. Give me another weak acid. HF is a weak acid. So if I combined that or had it with, I need a salt with its conjugate base. What's one? NaF. All right, that's a buffer. All right, but now let's do another weak base one. Give me another weak base. What's the most common one we use? NH3 is the weak base. So what would be a salt that had its conjugate acid in it? Sure. Okay, so are we starting to see the pairings? As long as you have a weak acid or a weak base and a salt that contains the anion of the weak acid or weak base or cation of the weak base, right? You have a buffer. That's what makes up a buffer. Okay. You okay with that? That's just the definition. Well, and recognizing them, I don't know, it gets easier as you do it. But anyway, all right. They basically it's a common ion thing. They're really just common ion problems. What does common ion mean? Yeah, they have same ion. Somewhere they have an ion in common. And it does, right? All of these pairs have an ion in common, right? There's the NO2, there's the NO2. Here's this piece, there's that piece, there's that piece, there, right? They have something in common. All right, so, because what happens to NH3, if it's functioning as a base, by definition, what does it have to do? Yeah, it has to take on an H plus, right? It has to add an H plus. So it really adds the H plus from the water. And you have the hydroxide. So this, whoops, it's not writing. Ugh, come on, thing. All right, this is the base. This is the acid. Now this is the conjugate acid. See it? And then this is the conjugate base. But the only part we care about is that we have this and this. If we have both of those in a solution, we have a buffer. And we do, right? Because that's what we have. We have the weak base and a salt that contains its anion. I mean, it's cation. I'm sorry. It's cation in that case. Okay. Good? Sort of? All right, let's look at the sample problem on your notes at the beginning. It says sample 1. Let's ignore the first sentence because really we're going to just use that to compare to. So let's look at the second sentence. It says calculate the H plus concentration of the H plus in solution containing 1 molar HF and 1 molar NaF. And then they give us the Ka for HF is 7.2 times 10 to the negative 4th. They want us to find the H plus concentration. All right, do exactly the same thing you've always done. What are our major species in solution? HF, water, what else? Oh, but how does NaF mostly exist in solution? As ions, right. So it's Na plus and it's F minus. Okay, now you have to decide which one of these is going to dictate the pH. How are we going to know? The K's, right. All right, so this one we know is a weak acid, and we know its Ka is 7.2 times 10 to the minus 4th. All right, we know water's water, and we know its Kw is 1 times 10 to the negative 14th. What about Na? It's from a strong base, so it is functioning as a conjugate acid, but will it do anything? It won't affect the pH because it's from a strong base. All right, so the K would be nothing practically, right? All right, and then F minus came from what? A weak acid, so it is a conjugate base, so it's functioning as a base, so I need this Kb to be able to compare. All right, back to this, in the math to the salts, we saw that Ka times Kb equals Kw, right? This only works for a pair, though, like for a weak acid and its conjugate base. But that's what we have here. So we have, if you know the Ka of HF, then you can find the Kb of F minus with that equation. So Kb is going to equal 1 times 10 to the negative 14th divided by 7.2 times 10 to the negative 4th. We're going to get something around 10 to the negative 9th, 10th, right? What do we get? 1.39 times 10 to the negative 9th? Is that what you said? Oh, negative 11. I went the wrong way. Sorry. Negative 11. Okay, so now do I have it right? Okay, so Kb for this thing is 1.39 times 10 to the negative 11. Which one's bigger? Ka. So this is what's going to affect the pH. The only thing is, this ion is in common with that, right? Because when I write the equilibrium for HF, I get H plus and F minus. The only difference is it's just not 0 at the beginning, right? HF is 1 molar, H plus is 0, but F minus is what? 1 molar, because we assume that this salt completely dissociates. It's soluble, so it completely dissociates, so it's 1 molar. That's why it's called a common ion problem. You have some ion in solution in common with the acid. So it's still going to shift right. Right, there's our ice table. And then so we have Ka, which is 7.2 times 10 to the negative fourth, is going to equal x times 1 plus x over 1 minus x. And what are we going to assume about those plus and minus x's? They're negligible, so that's 1 divided by 1. So x is going to equal 7.2 times 10 to the negative fourth, which is the H plus concentration, which is what they asked us to find. How does that concentration compare to that first sentence? That first sentence says a 1 molar solution of HF, so nothing else in the solution but HF, dissociates to give 2.7 times 10 to the negative second molar H plus ions. What happened when we had this common ion in there? What happened to our H plus? It decreased, right? So the weak acid still dissociated some. It still shifted right, but did it shift as right as far as it would have if there were no F? No, and that's the point, is that it didn't shift quite as far. That's what a common ion does, is it keeps it from shifting quite as far to the right. All right, so let's look at the buffer sample 2 problem, now that we kind of know what a buffer is. And it tells us it's a buffered solution. But even if it didn't, it says we have 0.5 molar acetic acid. We'll write it this way today. And a 0.5 molar sodium acetate solution. Calculate the pH. All right, what are your major species? All right, well, start with this one on the left. What is that? A what? A weak acid. So does it stay together or split apart? For the most part, it stays together. What about this one? Dissociates completely because it's an ionic compound. And then what else is left? Water. Okay, which one's going to dictate the pH? It should be and will get more obvious to you that since this part matches this, that this is a buffer problem. Okay, and all right, but this one's a weak acid. And we know it's Ka somewhere. Did they give it to us? Yes, 1.8 times 10 to the negative fifth. All right, what about Na? What did it come from? Strong base. So is it going to affect the pH? Nope. All right, and then this came from what? Okay, so it is functioning as a base. So it's the conjugate base. So we would have to know it's Kb. And then we know Kw of water is 1 times 10 to the negative 14th. Can you tell without doing the math which one's going to dictate? Yeah, because why? Yeah, the KB's got to be somewhere times 10 to the negative ninth or something, yes? Because when I take 1 times 10 to the negative 14 and divide by 1.8 times 10 to the negative fifth, this is going to be somewhere around 10 to the negative ninth or something. So this one's definitely going to be smaller, and I think it comes out 5.6 times 10 to the negative 10th, actually. So this one is smaller. So this is the one that's going to dictate the equilibrium in the pH. So now you write your equilibrium. What will that equation be? And? Right. Perfect. Now you can set up your ice table. Or if you don't need ice, I can't draw a straight line. If you don't need ice tables by now, that's fine too. So 0.5, 0, and guess what? There's 0.5 of this. Minus x plus x plus x. So Ka, which is 1.8 times 10 to the negative 5th, is equal to x times 0.5. You can't read that. Plus x over 0.5 minus x. K is really small, so we're going to ignore those. This ends up being 0.5 divided by 0.5, which ends up being 1. So x happens to equal 1.8 times 10 to the negative 5th, which is the H plus concentration. So how do we find the pH? Negative log of 1.8 times 10 to the negative 5th. Which should be about what, even without your calculators? Should be a little under 5, right? So 4.8-ish, maybe? Because this is almost a 2. I don't know. See what you get on your calculator. 4.74. Not writing. 4.74. Okay, the math part is not your problem at this point. You get this ice table and you probably get this by now. That's not your problem. Your problem is going to be getting here. That's where the hard part lies. What's in solution? What do I do with it? Right? And again, it's obvious to some extent, but it's obvious to me because I've seen it for 15 years, right? It's not as obvious to you. So that's why writing these major species will help significantly. When you start mixing up the acids, the bases, the salts, right, you start getting a mess. So if you can figure out what's really in solution and what's doing what, your life will be easier. Okay? All right, one equation that is kind of handy, that is not on the AP equation sheet. It's not, and in fact, you're not expected to do it because you can do it with an ice table. But if you want to use it, you are welcome to use it. It's this Henderson-Hasselbalch equation. It's pH equals the pKa plus the log. And I always write it just base over acid. Okay. What's pKa? It's the negative log of the Ka. Just like pH is the negative log of the H plus concentration, POH is the negative log of the OH minus concentration, the pKa is the negative log of the Ka. So if you know the Ka and you can recognize, let's go back and do, well, no, not that one. Let's do, look at sample problem 4 right under that Henderson-Hasselbalch. We'll come back to the other one in a minute. It says calculate the pH of a 0.75 lactic acid. I don't know what that is. Do you? Do I care? We're going to call it HLA. All I care is that the H comes off, right, for an acid. I don't know what lactate is off the top of my head. Does anybody else? Okay, well, instead of Googling it, we'll just use HLA. So we'll go, HLA is our lactic acid. It's 0.75 molar, and we have 0.25 molar Na lactate. So we'll just call it NaLa. And we know the Ka for the lactic acid is 1.4 times 10 to the negative 4th. All right, we can set it all up in an ice table just like we did on the last one. But let's do it in this, just to do it. The pH is equal to the pKa. So what am I going to do there? Of 1.4 times 10 to the negative fourth plus the log, okay, of the base over the acid. What part's functioning as the base? Yeah, that conjugate right there, right? What's its concentration? 0.25, right. Over the acid, well, what's the acid's concentration? All right, so do that in your calculator. Yes, if this, you're saying if there was like this with a 2 right there, yeah, it would be 0.5 then. You would double. You would double the concentration. All right, what do you get for pH? 3.38. All right, now let's do it with the ice table. What would it look like in an ice table? You don't have to write it on your paper. What would this initial concentration be? And this one would be 0.25, and this would be 0 minus x plus x plus x. So 0.75 minus x, 0.25 plus x. So Ka, which is 1.4 times 10 to the negative fourth, is going to equal x times 0.25 minus x over 0.75 minus x, and we're going to get rid of those x's. Okay, so 1.4 times 0.75 divided by 0.25 is going to give you x. What do you get for x? What? Times for x? What do you get for x? 1.4 times 10 to the negative fourth times 0.75 divided by 0.25. To the negative fourth. Okay, I was like, it's got to be times something. All right, 10 times 10 to the negative fourth. Well, this is the H plus concentration. So now find the pH. Take the negative log of that. Oh, guess what? Same thing. Okay, so you can memorize it and use it and do it in that little short of time. If you want to, that's fine. Or you can always continue to do the ice tables and it will work. Yeah, your ice table has to be the weak acid. Yeah. And really, I didn't write out all the major species, but you would have HLA, you would have Na plus, you would have La minus, and then you would have water. And this number is going to be bigger than any of them, so that's the one that dictated the pH. So that's the one you needed to write the ice table for. Okay, so either way is fine. But if you want to use Henderson-Hasselbalch, you have to memorize the equation because it's not on the equation sheet. But they will not, I mean, the AP test will take it. They're just not going to give it to you. They're not going to give you the equation, but they will, you can use it. All right, so if you recognize it's a buffer, you can use that. All right, so the whole point of buffers, what did we say their function was in the first place? All right, resist a change in pH. All right, so we have to see this happen. This is probably the hardest thing. This problem's probably the hardest one to understand in AP Chem. Now, when you throw this in with titrations, it's even harder, but otherwise this has to make sense. Okay, so we have a buffer solution, right, that has a weak acid and is salt with its conjugate base. So we have this buffered solution sitting there. What happens if we throw some NaOH into that buffered solution? It's going to do something, right? That NaOH is going to react with something, but somehow it's not going to change the pH, right? Because if I throw NaOH in just water, does it change the pH? Yeah, significantly, right? It's a strong base. It's going to make the pH go up, right? Well, but if I throw NaOH in a buffer solution, it shouldn't change the pH much at all. So that means it has to be reacting with something. Agree? And that's what you're going to see. All right, so let's look at this sample problem 3. All right. We have calculate the pH change that occurs when 0.01 moles of solid NaOH is added to 1 liter of the buffer solution. So it must have been the one before. What did we have before?
What problem is this?
Sample problem 3 on the back page with all those graphics things. Okay. All right, so we're going to assume it's into the buffered solution from sample problem 2. So that says that we put it in 0.5 molar acetic acid, and it was 0.5 molar in sodium acetate. Okay, and they gave us the Ka was 1.8 times 10 to the negative fifth for the acetic acid. All right, list our major species. How do these things exist?
Water.
Okay, water. That's the easy one. All right, NaOH. What is it? Strong base. So how does it exist mainly? Na plus, OH minus. All right. Acetic acid. How does it mainly exist? It's a weak acid, so it mainly exists as its molecule, right? Then we have this, NaC2H3O2. It's an ionic compound. It's not a strong acid or strong base. It's an ionic compound. But because it's an ionic compound, what does it do? All right, so how does it mainly exist? So more Na pluses. I'm not going to list it since it's already listed. All right, so there's our players basically, right? What you should start to recognize is you have this weak acid and you see something very similar to it, right? And that's probably a buffer solution. However, I got this hydroxide in here and this Na. Is the Na going to do anything for us? It's not going to dictate the pH because it's the, right? So, and then we've got water. So these three things, if I just had those three things, what would dictate the pH? That strong base. But that, I think so. Yeah, right here on this page. Because it says in the buffered solution. So I'm assuming that buffered solution was from sample problem 2, the one before it. It said they put 0.01 moles into the buffered solution. So I'm assuming that that's the buffered solution from the problem before. So that's where that's coming from. All right, what's going to happen is you've got to look for a reaction that's going to happen before this thing goes to equilibrium. What are the most likely things to happen first or to react first? The strongest acid and base will the strongest acid will react with the strongest base. What's the strongest base in there? The OH. What is it going to react with? Yeah, because it's a stronger acid than water, right? How do I know it's a stronger acid than water? Because the Ka is bigger than water, right? So what happens when you start putting stuff into a buffer is it ends up being a two-step problem. It ends up being a stoichiometry problem, and then it ends up being an equilibrium problem. So you really set up, and I kind of use ice tables for both, but what's the difference between saying something is stoichiometry versus something is equilibrium? What's the difference? Right. This one goes to completion. So the arrow does not go back and forth. In equilibrium, the arrow goes back and forth, and we use the ice tables to figure out how much change we're going to get, right? All right. So let's do the stoichiometric part first. And stoichiometry is based on moles. So if you, and it be real careful, sometimes they'll add, this one they did not. They put a solid in 1 liter of solution and it's 1 liter all the way. So we're fine. But be careful because if they put in, 500 milliliters of NaOH, then those volumes add. That's where the titration gets even harder, right? Because you added volume as well. We did not in this problem, so it's not quite as hard to deal with. All right, so what's the stoichiometry? What's going to react? And what is it going to make?
Water and acetate minus.
Right. All right, so I'm going to use an ice table, but I'm also realizing I'm doing stoichiometry. And this one I do in moles. In this case, we can do it in molarity, but we're going to do it in moles because we had that solid. Oh, I forgot my plus. Okay. All right, what's the original concentration of the OH minus? 0.01. Oh, not concentration, moles. Same thing in this case, but anyway, 0.01 moles. All right, how many moles do I have of the acetic acid though? I do have 0.5 moles. Why do I have 0.5 moles and 0.5 molar? It's a 1 liter solution, right? I don't really care about this water. What about this acetate? No, 0.5 again. Okay, if this is stoichiometry, it has to go to completion. What does that mean? It will only go this way, so it has to shift right. But what else does it mean? Okay, this is minus, this is a plus. What were you saying, Lexi? They have to get used up. Which one of those two is going to get used up? The OH. So minus 0.01. And since these are 1 to 1 to 1, how nice, right? This will be minus 0.01 as well. And this will be plus 0.01. So this will go to 0. This will change to 0.49. This will change to 0.51. Okay, all that did, oops, sorry, I was trying to erase the bottom of that whole thing. All that did was give us where to start our equilibrium. So basically you assume that the strong acid or strong base that was put in reacts with something completely, and then the weak acid or weak base that makes up the buffer shifts back to equilibrium. So now what's left in our solution? All right, we still have water. Do we have any more hydroxides? No. We still have Na pluses. Do we care about them? No. But we don't have any more hydroxides, right? They're gone. And we have HC2H3O2 and we have C2H3O2 minus. What's now dictating the pH? Yeah, this thing, right? So now I have to write the equilibrium with that acid. So same thing you've been doing. Oh, put the 2 at the top. But what are our initial concentrations going to be? Oh, goodness, I really drew that bad. Yeah, what you got right here. Exactly. You're going to carry down what you got in the stoichiometry down here. Now, technically, I'm in moles up here. And I want to be in molarity down here. In this case, it's the same thing because we have 1 liter and we didn't change anything. So this is 0.49 molar. This is 0. This is 0.51 molar. Still going to shift right. So 0.49 minus x, x, and 0.51 plus x. So our Ka, which is 1.8 times 10 to the negative 5th, is going to equal x times 0.51 plus x over 0.49 minus x. We're going to get rid of those x's. Guess what? That's really close to 1, isn't it? Yeah, so when I divide that underneath this 1.8, does this 1.8 number change very much? Not very much at all. And if it doesn't change, it's the H plus concentration. Does the pH change? Not much. And that's the point. All right, so tell me what X ends up being. Still ends up being 1.8. 1.72 times 10 to the negative fifth. And then you have to find the pH of that, which ends up being what? 4.76. What was our pH in the buffer to begin with? I don't have to go back a couple of pages. 4.74, right? And when we dumped in this strong base, it went to 4.76. Did the pH change? Not much. A little, but not much. And the whole thing is you have an acid and a base in there. You have an acid in this conjugate base. So if you dump in a base, it can react with the acid. If you dumped in an acid, it could react with the base, right? And it doesn't shift the pH very much because it doesn't change those concentrations all that much. Uh-huh. This isn't water. This is H plus. Here, that's H plus. My 0 ran into my H plus because I didn't draw a very good straight line. Sorry. That's just my writing. Okay, so, I mean, did I prove to you that a buffer resists the change in pH? Okay, that's the hard problem. If you put something in a buffer, it is basically two problems. You have to do a stoichiometry problem to completion, then you have to use those numbers in an ice table to figure out equilibrium. Okay? Just if you recognize it's a buffer and it's a multiple choice, yeah, you can pick the number that's the closest to the original pH. Sure. It probably wouldn't be a multiple choice question. Okay, so we think we got it? You want to try one on your own? Here, let me